Hi guys, chapter 24, we're going to talk all about magnetism. Just a little fun facts on this slide here about how magnetism got its start, discovery, all of that good stuff. Interesting fun facts. My favorite is the one about the Chinese using a magnet for a compass as early as the 12th century. Now, changing gears, in last chapter we talked about force between two static charges and how that depends on the size of those charges and how far apart they are. And that was specified by Coulomb's law. But Coulomb's law is not the whole story, because what if those charges are moving? Right? Well, then the electrical force on them becomes a lot more complicated, and there's magnetism involved when charges start moving. Right? We're going to discover that this time around. Alright, starting simply with what is a magnet. Alright, well, we know there's magnetic forces. I'm sure you guys have all played with your refrigerator magnets and know they stick together and you gotta pull them apart. Alright, well, magnetic force is just like charges. They repel and attract each other. Alright, but instead of having positive and negatives like we do on electric charges, we have North Pole and South Pole with magnets. Alright, same deal goes though. If you have two of the same poles, they're going to repulse each other. If you have opposite poles, they're going to attract each other. Okay? Now, we could have a solo charge, one lone electron out there when we were talking in the last chapter. But you can't do that with magnets. You can't have just one pole. Right? If you chop a magnet into little tiny bits, you're going to have tiny little magnets still with two poles on them. We can't get just one magnet or one pole for a magnet. Here's some examples of magnets. You got the horseshoe magnet, and then you got simple bar magnets here. Alright. Now, when you were playing with those refrigerator magnets as a kid, when you got those magnets close together, you started feeling the force, whether it was attraction or repulsion, you started feeling it. And they weren't even touching, right? This is that force field that we talked about before, right? In this case, it's called a magnetic field. Alright, now the magnetic fields, you can see by the lines made here by the iron filings, how they swirl around and now they're created. Alright, well, a magnetic field travels from a north pole around to the south pole and then back through the magnet and then keeps going around. Alright, now we couldn't see an electric field, but the cool thing with magnets is you can shake some iron filings out like in this picture and you can actually see the magnetic field. Alright, now while the magnetic field is denser, the lines are closer together, like around the poles here, that's where the magnetic field is the strongest. Okay? Now, how do we get a magnet? How do we get this? Well, the electrons that are around the nucleus, right out there in the cloud, those electrons are spinning. And that is the main contributor to magnetism. If we can get them all spinning in the same way, then that will create a really strong magnet. Alright? Now, each object has domains, completely random, but these domains are made of billions of atoms, and these atoms have all these electrons, right? If we put an object, especially something with iron in it that's got magnetic properties, right? So like in this picture, unmagnetized iron, right? You can see all the random motion of the electrons and domains in there, right? Well, if we put it in the presence of a really strong magnet, bam, look what happens. They all line up and we get a strong magnet. And we can even chop it into pieces and have two strong magnets or three or whatever. Alright? Now, you can make a temporary magnet or a permanent magnet. Alright? Now, a permanent magnet will stay aligned even when the magnet that got all of its electrons going in the same way is removed. Right? It'll stay a magnet. That's permanent. If you remove the strong magnet that made all the domains line up and then all the domains go back random again, well, that's temporary. Right? So it all depends on that strength and how well everything stays aligned, whether you get a permanent or temporary. And it also depends on how you make it, too. Okay? So electricity and magnetism, they're connected. They're related. Oersted made the first discovery. He had a compass lying close to just a wire that was carrying current, and he noticed that the compass deflected, and when he moved it at different places around that wire, it deflected differently. And what he discovered was that there is a magnetic field all around that electric current. Well, what is an electric current? Moving charges. So any moving charge has its own magnetic field. And here's what it looks like. You got a current carrying wire, right? Moving charges going through there. It has its own magnetic field that looks like concentric circles around. All right? Now how can we take advantage of that magnetic field for us? Well, we can loop the wire, because look what happens when you loop the wire. It still has its own magnetic field going around, but now look how concentrated they are, right? A lot of strength right there. And here's something else you can look at. See, you see the concentric circles going around that wire? Well, look what happens when we loop it. Got a lot more density right there. Well, look what happens when we loop it a lot. Look at the strength of that. That's all magnetic strength in there, all right? So the more loops you put in, the stronger magnetic field you get. Well, this has a special name. You just created an electromagnet, all right? So how can we make our electromagnetic stronger? Our electromagnetic field stronger? Well, you can increase the current. You can increase how many loops of wire that you have. Or instead of leaving inside the loops empty like in this picture, you put an iron bar inside there. Remember what happens when you put iron in the presence of a strong magnetic field? It becomes magnetic, right? So then it's like you got two magnets in there, increasing your field. These electromagnets have so many applications, all right? From levitating high-speed trains, like in this picture, to particle beam accelerators, to making your credit cards work when they swipe through the cash register, to, what are those things? Security gates you go through at the airport. All those things run off electromagnetics. Did I go to the right screen? Yep, sorry. All right. Well, what happens when we put the magnetic field that current running through a wire has in the presence of an extra magnet, like in these pictures? Well, you get a force, all right? A deflecting force, really. So if you have this wire here, right? Current's running into the picture there, right? And we have this horseshoe magnet we bring in, right? So now we've got two magnetic fields. Well, they're going to interact with each other, right? So the magnetic field runs from north to south. You see the way the blue arrows are going. And the current's going into the page, and the pink arrow tells us that there's going to be a force of deflection down, all right? And I've even got a video here that shows you that, all right? Well, how can you determine the direction of the deflection? Well, it's a right-hand rule, all right? So, pick up your right hand, all right? Okay? And we are going to use our right-hand rule with this first picture here, okay? So I'm going to point my fingers into my computer screen, going the direction that that current is going, right? Now, I've got to curl my fingers, right? I've got to bend my fingers in the direction of that magnetic field, right? So, where's my camera? Sorry. So my magnetic field is going that way, right? This is hard because my camera is a mirror image of you, all right? So your current's going in, all right? Your magnetic field goes to the right. This is not going to work because my camera is mirrored. All right. So, anyway, current goes in, magnetic field is to my right, all right? And then you stick your thumb out and the force is down, okay? Sorry about the camera doing mirror images, but we'll practice it in lab, okay? That's the direction of the deflection. Well, how is this useful other than just like being something cool to watch like in the video? Well, it also lent to the invention of electric meters and electric motors and all that stuff. All right, so let's talk about meters here first off. A galvanometer is more of an indicator than a meter. It just tells you if there's a current detected. Now, an ammeter actually measures current, and a voltmeter actually measures voltage. And then you can get you a handy-dandy multimeter that measures a multitude of things, right? But if you take a galvanometer and we do a little modification to it, we can make a really simple, crude electric motor, which is pictured here, all right? So we have a loop of wire here, our yellow loop of wire, and it's carrying a current from our battery here, all right? Then we place that loop inside this big horseshoe magnet, okay? Now we make the current change direction every time the loop makes a half turn, okay? And that will change the direction of that magnetic deflection and thus actually keep that loop rotating continuously like a motor has to. A motor has to continuously turn over, right? Now, if we didn't change the direction of the current, right, then that loop would sit there and do this, right? It wouldn't keep going just around and around because it would be deflected one way from when the current was running this way. But look what happens when you get to the top side of the loop. Now the current's running back out. It's in a different direction, so your direction of your current flips the direction of that deflecting force, and you would just have that loop sitting there doing this instead of continuously turning. All right? This crude electric motor actually runs some clocks and some other little simple devices like that. All right? Just some little tidbits here. The Earth has a magnetic field all around it, as you probably know, right? But it's due to electric currents from different radioactivity in the core, all right? Well, scientists actually think that the Earth's magnetic field reverses every few million years, right? That's pretty cool. Now, the universe has charged particles, cosmic rays, shooting stars, etc., running through the space. Well, cosmic radiation, as you know, is hazardous to astronauts, and most cosmic rays are deflected away from Earth by our magnetic field. But some of them can get trapped in the outer reaches of the magnetic field of Earth, and these are called Van Allen radiation belts. All right. Well, if there's a disturbance in the magnetic field, right, like if there's storms on the sun that hurl these charged particles out like great geyser fountains, then some of them will pass really close to Earth and get trapped in the magnetic field. All right, they specifically get trapped near our magnetic poles. All right, which North Pole, South Pole, is because, as you saw in the picture before, the poles are where the magnetic field is the strongest. Well, they'll get trapped there, and then they'll start bouncing around and making spiral patterns from all the deflections due to the magnetic field, and that's when you get these cool little light shows called the Aurora Borealis if you're at the North Pole, or the Aurora Australis if you're at the South Pole. Pretty cool. All right. Well, certain bacteria produce single domain grains of a magnetite that is really equivalent to iron ore. So they can string together and form an internal compass. All right. Now this is actually seen in some animals, all right, like pigeons, turtles, some fish. This is how they migrate and find their way back to the same place year after year for like turtles or fish to spawn, birds, migratory patterns for this change in the seasons, all because they make an internal compass thanks to magnetic fields. Pretty cool. All right. Watch the videos, check out the extra credit, read your book. If you have any questions, you know where to find me. See you guys next time.